um, you declare what your depth area is going to be, and that's the booklet you get. So people used to be, for example, it used to be very common water resources like the hydraulics and hydrology side, or environmental, because there were two depth areas that were different and construction was not in the picture yet. And people used to be on the fence and decide at the time of the test that on this booklet, the environmental set looks easier, so I'll do that one. You can no longer do that, which is in a way a good thing because you commit to a particular depth area and you study for it. But at the same time, then make sure that you study or you understand exactly the layout of topics in that particular depth area, and of course the breadth area, which you have to do anyway, what they are. And if it means that in certain places you have to quote unquote cut corners, meaning that there is a particular thing that just seems very old, very foreign, will take a whole lot of work to bring it up to snuff. If there is such an area compared to others, and the likelihood of that is just as much as other areas, then your effort should probably go in other areas. You know, if you're unlucky enough to get a question from that area, then you miss one question, but you put in your efforts into things that where you have a greater shot of scoring points. So you have to kind of choose your battles on this, because I'm sure everyone in this group is balancing work, family. It's not like college kids. So you have limited time and you have to tune your studying to that. So I'm going to upload the syllabi. If you don't have them already, you can download them, upload them as they are today. And a couple of them have been tuned here and there. And I'll upload other documents and I'm going to keep a list of everything I'm uploading to the Google Drive. So if anyone wants to take a look at that list as well, they don't have to download everything from there, because again, as far as references are concerned, some people believe in more is more philosophy. I don't think so. Some people go in with like millions of books, stuff that they haven't touched in the last 5 years. They take them in anyway. And what that does is it gives you a false sense of security about every single question, saying I have it somewhere and I can find it if I had enough time. But you don't have enough time, right? And you get trapped into that a few times. Pretty soon you are hunting around in a totally unfamiliar document for something, and you've spent like 10-15 minutes on a single question. It would probably be better in that situation not to have anything where you could look, because then you could just move on and do something else instead of wasting all that time. So having things with you that you have used, that you're familiar with, is great. Having things that you haven't touched in the last 4 or 5 years, it's definitely not, in my opinion. More is not more in that case. So let's start with our strategy in this group. I'm just going to take a couple more minutes on generalities. In this group, all 5 sub-disciplines are more or less uniformly distributed. So something that I can do in terms of course planning is, for example, the last time or the time before last I did the course, there was nobody from structural depth, right? And when that happens, then we can tune our time to that particular audience, in that there is no point in discussing concrete design and steel design and bridge design and this and that, because those things have really zero probability of showing up on the AM questions. And so we took away those 2 lectures and we did other things. For example, maybe water and environmental was overrepresented in that group. So we did an extra class on environmental, and so on. So this time we don't have that option. So we will go through in this order for both AM and PM. So in the and you might have seen that in the document: structural, geotech, water, And when I say water, this is strictly hydraulics and hydrology. This is for the AM topics, so there are no environmental questions whatsoever. Transportation and construction. So we'll go through these in lectures. I said in my document that I sent out in lectures 1 to 10, but transportation is, as of a couple of exams ago, is severely cut back in the AM as well. There are only 3 true transportation questions, right? And in fact, at the construction was expanded quite a bit at the expense of transportation in the AM. So lectures 1 to 9 should actually cover us for the AM questions in these. And then 10 to 20, the remaining 11 lectures we will, because structural, if you have to go into depth, will require maybe a tad more than a couple of lectures. So we may not be able to do two, and 10 lectures for the PM. We may have to need more time. And then we'll recap everything at the end, of course. So these are for the AM topics. We'll go through in that order. The reason for putting construction at the very end of the list is, and this will be lectures, 8 and 9, I guess. And this will be 7 and so on. Is because construction is such a cross-disciplinary area that many things that are in the syllabus under the umbrella of construction are already discussed under the umbrella of structures or geotech or transportation and so on. So once we get to this, there may be only again, I'm making air quote signs, the core transportation topics that have not been talked about elsewhere, and so we talk about them at the end of the cluster. All right, so that's all the general chit-chat. So let's talk about what is likely to be in the structural breadth questions. Now, if you look at the at the breadth exam syllabus, under structural mechanics, they have dead and live loads, so load types. When it comes to this particular broad heading, sometimes they use headings that are really broad. Dead and live loads, they're not really expecting you to know things like, what does ASCE 7 say about appropriate live loads for a commercial building or for a convocation center or whatever. They're not really expecting that. As far as I've heard, and I've not heard a single person who has said opposite to this, and that is, for the AM question, for the AM exam, you don't need to open a single code reference, code or specification. Something like Lindbergh's book or my book or something other equivalent book that goes into review of topics and basically that should be more than enough. You don't really need, there are going to be no lookup questions and so on in the AM. When they talk about dead and live loads as a topic, therefore, in the AM syllabus, they're talking about the questions that might depend on the transient nature of live loads, meaning these are permanent and these are transient. So the question may be of the nature, what would be the worst loading combination for designing the footing for this particular building? And if you notice that putting the live load on would actually cause overturning and reduce the hang on a second. So there was a sample question like this, and the dead and live loads were transferred to the building like this. And this was just a single story building frame. And the question asked, what would be the worst load combination for designing, for example, this footing, right? Now, the reason I am all distracted is because I just spilled some coffee on my tablet. Great. Oh no, don't do that. All right, so the options were dead load only, which of course will be present all the time. Option 2 was dead plus live load. Option 3 was dead plus wind load, and option 4 was dead plus live plus wind. Now, of course, the live and wind are transient loads, right? Live and wind are transient. Notice that they are on or off in these different scenarios. In option 2, wind is off, live load is on. In option 3, wind is on, live load is off, and so on. But the dead load is present every single option. You don't have any choice about that. It's permanent. So the question is, which ones of these, live and wind, will contribute to what you're trying to design for? Now, if it comes to the footing here can be designed for compression, it can be designed for bearing. In other words, bearing compression. Oh, another thing is, like everybody else, my handwriting has a default font size, so I sometimes will write, in spite of reminders, will write maybe a little too small. Just tell me, okay, through the chat window or something, can you write a little bit bigger? Because of course, later on, when I send you this file, and that's another thing too, concentrate on participating and listening rather than writing everything down, because what I do is, right after the class is over, I send you this Word document or a PDF from it. So that you don't have to spend your time writing down every single thing I write down. But anything you notice beyond what I'm saying that you think is useful to make a note of, do so. But what I'm saying is at the time of the writing, if I'm writing too small, let me know. Okay, I'll try to remember. So you could design this particular footing for bearing compression, right, the bearing capacity of that soil, or you could also design it for the unlikely but possible situation of uplift if these loads causing uplift are going to be very strong. Now you notice that the wind load definitely causes uplift at this footing and causes bearing on the far side footing. And typically for wind loads, what you'll do is you'll design the structure for a reversible wind load, meaning that it could also go the other way, right to left, in which case the scenario would reverse, uplift on the right and compression, added compression on the left. The live load, because it is off center, can cause compression, but it can also cause overturning at this footing. So the live load actually will contribute to overturning at this footing as well. So the question has to be clear. What is it that we are putting this load combination for? Are we trying to figure out the worst worst uplift at that footing? In which case, we want to position the loads in such a way that they produce uplift, right? If we are trying to design for the worst bearing compression, then we want to choose our loads such that the bearing compression is maximum, which of course will be greater on this side than on this side, right or left. Okay, so the question, make sure you understand the intent of the question. And so that is, I think, what they're talking about under this dead and live loads category, just understanding the difference between the nature of these loads. All right. Oh, another thing which, of course, I mentioned in the document I sent out is the NCES sample questions. I mean, there's a whole bunch of different sample question sets out there. NCS's sample questions are obviously the ones that everyone should at least have a look at even if they don't own it. Because these are the guys that are writing the exam, they're creating the exam, and so you want to get their sense of what they're saying is questions of reasonable difficulty, right? So there's a lot of disagreement between question sets. People complain sometimes For example, people complain up and down about my sample question sets that are out, and that is because they say these are much harder than the actual test. Well, I didn't want to waste a whole publication publishing questions all on a low level just because they would be exam-like. My intent was in those exams or practice exams was to give people a set of questions to practice with, but at the same time, maybe go into depth with some of the questions so that it makes them think and maybe raise a flag for somebody saying that this is something I hadn't thought of, so let me go and review that a little bit. So when I do that, I get complaints, but I've learned to live with that complaint. That's okay. But the NCS sample questions, people always say that they're the most representative of the actual test. Now, the way this question, well, not this question, but a numerical question that involves numbers, the way that a question would be worded in NCS's sample questions and on this test is the maximum, I'm just making up something, the maximum distributed load intensity in pounds per foot on the beam is most nearly, and then they'll give you 4 choices, right? And they'll give you like 6,000, 8,000, etc. Now, a couple of things to make sure that you're aware of. First of all, the units are embedded in that question. They are not repeated here. They're just pure numbers in the answer, typically, right? That's one thing. So if you have a units issue, meaning that you were right from the beginning of that problem, for whatever reason, you're using different units. Let's say instead of pounds, you're using kips, and that's an easy one to spot. But when you work out your answers will be in the neighborhood of 6 and 8 and 5 and so on, not 6,000 and 8,000, because you're working with kips per foot, right? That one's easy to see. Sometimes the foot and inch mistake, that's not so easy to see, and in fact it's not such a blatant difference, not a factor of 1,000 but a factor of 12. So that is a common source of mistake, right? Not being careful with that, not losing sight of what the units desired are. Second is this thing about most nearly. Now, sometimes most nearly is just that. It's the number closest to your calculated answer. So if you calculated it, it turned out to be 2573 and there is a 2500, that's close enough, right? If you look at the percent difference, that's not very far off. However, sometimes it means you got to go down, sometimes it means you need to go up. So it could be possibly one nearest number. A good example might be they say that the ADT on a particular bridge in the year 2000 was 35,000, and assuming a population growth of 3%, what would you project the ADT to be in 2020? We all wish we had a question like that. 15 seconds, but basically what you're doing is geometric growth according to population of the traffic. And you come up with a number, and you come up with a weird number, right? 35679 or something. Now, they are not going to have that as on the answer choices. Maybe they have 35700, right? That is close enough, and in that case, there is no reason to go up or down. You just choose the nearest number. The other option is when some kind of a strength issue is involved. For example, here, this says maybe the criterion in this particular problem was a certain deflection cannot be exceeded. And they're saying if the deflection is limited to this number, then what is the maximum distributed load you can put on the beam? In that case, you have to stay under the calculated value because the number that you calculated represents an upper bound. And for that distributed load, you will just hit the critical deflection. If the load is any heavier, the deflection will be exceeded, and it's a not a strength exceedance, but it's a deflection exceedance, but sometimes you go lower, right? And sometimes you go higher. An example of that might be, for example, in a wastewater treatment plant, they say that filters are designed for an optimum loading of 100 gallons per day per square foot or something like that. And then you figure out what is the area of filters required, and from that you figure out that you need 6.3 filters. But you can't use 6.3 filters, your choices are 6 or 7. In that case, you would have to go higher to 7 filters, because if you go down to 6, even though it's closer to your 6.3, the load on the filter will be exceeded above the critical value, right? So in that case, you can go higher to the next integer value. So you have to be careful, because these are scenarios where you can do everything right about the problem, and you make a bad choice at the very end. And that's just terrible. Watch out for units is, if I could put in big font, watch out for units all the time. All right. Okay, so that's the first category in the syllabus. And then you have the second item is trusses. Typically, you can almost count for certainty that there will be at least one truss member force calculation problem. Method of joints, method of sections. Obviously, method of sections is more convenient. Why does it do that? Sorry. For example, here another thing, trusses by definition are all joints are hinged. And so there is another thing that that happens for hinged structures, no rigid connections between members, and that is the idea of zero force members. You can identify zero force members for hinged joints without doing a full analysis. Now, if you had an example such as, let's say, something like that, say a lateral load and a couple of gravity loads, 30 kips, 40 kips, 20 kips, and so on, pinned and roller connections at the supports, and joints designated A, B, C, D, E, F. All right, so if they ask for this particular problem, what is the member force in member, let's say, EF? So when you get a question like that, obviously they're on this exam, they're not asking you to solve the entire structure. They're asking a very specific one single member force. Typically, first of all, answer choices will be in pairs. At least I would put them that way. Like 25, most nearly and all that stuff in kips. So 25 compression, 25 tension, 33 compression, 33 tension. The point is that there are dual values, answer choices that are both 33 or both 25, and the distinction is one is compression, one is tension. So make sure that you're clear on that aspect, because if you're not, even after getting the number 25, if you're not clear on the difference between compression and tension, then you're still caught between two choices, right? A tension member, so if this is a joint and there is a member framing into it, then a tension force would always be pulling on the joint, pulls away, and a compression force would basically push in, right? So typically, I don't know about you, but I've always been used to just starting out with members designated as tension, draw them in as for pulling away from the joint, and then if the algebra gives me a negative value, then so be it. That means it's compression, right? Now, this is the member force that we have been asked for, member EF. Now we can see that we can go figure this one out and this one out and this one out and this one out and go through a path to get to that member, or you can do method of sections. Method of sections will be an easier way to get straight to it, and you'll have to make an appropriate section. Appropriate meaning that if you make a section that passes through too many members, for example, if I were to draw an alternate here, if I were to make a section that looks like this, that also cuts the structure into two halves, but notice that it cuts through 1, 2, 3, 4, 5 members altogether. So when I draw that free body diagram, I end up with 5 unknowns and I have only 3 equations of equilibrium. Method of joints, 3 equilibrium equations for each section. Whereas method of did I say method of joints? Method of sections. Method of joints is 2 equilibrium equations each joint. So that would be unsolvable. I could write down all my equations, but then I wouldn't be able to solve them, so there's no point in writing them down. And sometimes you have to take a convoluted path and make multiple sections. I doubt that there'll be anything like that on the PE. On the PE, typically, to answer the question, there'll be a clear choice that if I make this section that passes through 3 members, like this one passes, the black one, and so 3 is solvable because I get 3 equations for that section. So I can solve them, right? So not that I'm advising you to draw this as the less drawing and redrawing that you can get away with, the better you are, because all that takes time if done correctly. So this is, so how would you do this on the test? I would take a book or something that you have lying by your side, which you're not even using for this question, and just cover up the picture on the original booklet, question booklet, so that this is what you see, right? The figure below is what you see. Now, what you need is, we don't know these reactions. So in this particular case, we know this 30. We know this, there is a force here, F1, there is a force here, F2. Notice I've drawn all of them as tension. There's a force here, F3. This is the one we want. This is the one we have been asked about. And I could get away with, if you look at the two that I don't want, F1 and F2, and if I were to project them to meet at node C, if I took summation of moments about C and use that equilibrium equation, that would be the quickest way to solve for F3, wouldn't it? Because if I take moments about C, F1 and F2, no matter what they are going to disappear from that equation. And so I'll be able to solve for F3. I know the 30, but you notice that I do need these forces, or rather their moments will not disappear if I take moments about C. So I do need those. Sometimes you don't even need them. And if you can see, I think in the practice questions, there is one truss, a cantilever truss that looked like this. And it kind of, I'm going to try to, it kind of looked like this, right? There was like a pin and a roller, and there were loads here, and the question maybe was about this member, right? Notice that in that case, there is a great section that we can take. Looks very similar to what we are dealing with here. But if I deal with this side, the right side of that free body, of that cut, I don't even need my reactions. So that whole idea that when you're solving a structural problem, the first step is calculating reactions may not be true, particularly for cantilever structures. You may get away with not even knowing them, because if I cover up what's on the left of this cut, if I look at the right side, I have my three unknowns, and then I have known forces that are the joint loads that are given here. None of these are the unknown reactions. So I can solve that directly without even getting into the reactions. Typically happens for a cantilever structure, because in the cantilever structure, all your supports are on one side and the rest of the structure is on the other side, right? Here, however, for a simply supported structure, your supports are on either side. So if you make a cut, then regardless of whether you look at the left side of the cut or the right side of the cut, you have to deal with one of these reactions, A or D. So the first step here would be to find your reactions for the entire structure, and so for this case, for the entire structure, the internal details don't matter. What matters is the position and magnitude of the loadings. And once again, you can probably work off the original drawing. If you're taking moments about A, these don't matter either. And the only thing that would matter or show up in that equation is what is the moment of dy. Because if you're taking moments about A, then there are reactions at A, but they will drop out of that particular consideration. So once you practice these a little bit, you can get away with not even drawing this diagram. Know what I mean? At the beginning, if this is something that you haven't done in years and years and you don't do it as a regular part of your job, but you did do it and you were pretty clear on it. And so you can, while you're reviewing, it's okay if you're having to do this. But I would suggest that you keep practicing until you get to the point where you can look at this drawing and say, if I take moments about A, I usually will do an inventory. In other words, I'll say there is a force here that'll produce a moment term. There is a force here that'll produce a moment term. There is a reaction here that'll produce a moment term, and there is a force here. So I know I have four things to deal with. So if I take moments about A, summation of moments about A, and you have to keep yourself straight, adopt a sign convention. Doesn't matter which one, as long as you stay true to it. So clockwise positive, let's say I'm using. So taking moments about A. Oh, I didn't even give any dimensions here, did I? If I were to follow through, I would need to know that these are, sorry, making it messy. Let's say three bays, three panels at, let's say 20 feet each. And let's say the height of this is 10 feet. So then taking moments about A, I have a 30 kip load at a distance of 20 feet, and that would be clockwise, so positive. Then I have a 40 kip load at a distance of 40, that would also be clockwise, plus. Then I have the 20 at a height at a distance of 10, that's also positive. And then the dy will turn the other way, and that's counterclockwise about point A, and that is at a distance of 60, so minus 60 dy is equal to 0. So then you have a 1600, 2200, 2400, so dy is exactly 40 kips. And by looking at the distribution of the gravity loads 30 and 40, then ay must be 30. The total downward load is 70, dy turned out to be nice and 40. And AX is, by observation, obviously 20 going that way. The only thing that resists that is the 20 going that way. So that would be a minus 20. Minus meaning, if I presume the original to be going left to right, then it's going right to left. Okay, so now you have a reaction force here, which is 20, and a reaction force here, which is AY was 30. So now you can take moments about C, and moments about C would give you, again, let's keep to clockwise positive. Moments about C would give you F3 times the height of 10. And that would be negative because it's turning counterclockwise about C, right? Turning counterclockwise. This 30 at a distance of 20 is also turning counterclockwise. So there is a 30 times 20, which is negative. But then this 30 at a distance of 40 is positive. And then you have a 20 at a distance of 10, which is positive. So this then becomes your one equation that you need to solve instead of getting trapped in like simultaneous equations involving all three unknowns F1, F2, and F3. If you don't care about F1, F2, and F3 and only need to know F3, then this would be the shortest algebraic path to get that. Similarly, if you were only interested in F1, then you would want to take moments about this point, which I believe was E, right? No, F, sorry. So if you're interested in F1, you would want to take moments about the point where F2 and F3 disappear, or rather their moments that disappear. So to solve for F1, take summation of moments about F would be most convenient. Does that make sense? No problems with my handwriting, right? Are we good so far? Now, if you wanted F2 on the other hand, you would want to get rid of F1 and F3. Notice that F1 and F3, at least for this truss, they are parallel. So there is no intersection. There is no point where they intersect, and therefore take moments about that point. However, both F1 and F3 are horizontal, lined up with the x-axis. So to solve for F2, the best thing would be to take summation of Fy equal to 0. Because if you take summation of forces in the y direction, F2 of the 3 is the only one which has a y component, and so that is the only one that would show up. F1 and F3 are purely horizontal, they would drop out. Right? Now, force components which you'll have to deal with, obviously, when you're doing these, you have to take the component of a force and take moments of that component and so on. In statics, you first do a force at an angle theta, and you say this component is F cosine theta, and this is F sine theta, and so on. Now, when you look at that truss, one of the panels of that truss looked like this. It was a 10-foot high and a 20-foot long panel, right? It was part of a larger structure, looked like that. But let's say you're dealing with that particular member. You're dealing with that particular force, F2, on that angle. So obviously there is an angle here, theta, and you could, I guess, you could figure out what that theta is. Tan theta is 10 foot divided by 20 feet, 0.5, and from there you get theta is equal to whatever, 26.6 I think is the angle that gives you a 1:2 tangent, and then you use the sine and cosine of this. But you can say that that particular line is on a 1:2 slope, so Pythagorean theorem would say this is square root of 5. So if you've got a force that is F2, then the horizontal component would be 2 over square root of 5 F2, and the vertical component would be 1 over square root of 5 F2. So you can work directly with the ratios instead of having to go out to figure out the angle, and then from that angle, believe me, if you were to do sine and cosine of this angle, sine would give you 1 over square root of 5, and cosine would give you 2 over square root of 5. So you'd be back to those numbers anyway, but might as well just directly work with the ratios instead of going to the angle in terms of the angle, right? So I would say for force components, get used to using side ratios to calculate components. I've got to, I do this disclaimer all the time is I'm not looking at people's expressions. Obviously, we're sitting all over the place, different places, but sometimes I say things that makes half the class raise their eyebrows and say, why are you telling me this? This is obvious. I know this. And they are almost insulted. But I say these things because I have noticed mistakes made, and so on. So based on observing those things over the years, that people get get this ratio and this ratio mixed up. I mean, if you do that, then even if your method is perfect, you'll get the answer wrong. And sometimes on a multiple choice exam, especially, predictable mistakes like that, like interchanging sine and cosine, right? Or forgetting a minus sign, or forgetting to convert from inches to feet, or something like that, a predictable mistake will typically lead to one of the answer choices that's available there. So you never get a warning that you did something wrong because you landed on answer D, and you're pretty satisfied that went fine, and you move on. It's the random mistakes that are actually better because you get an answer that's nowhere in the four answer choices, and that makes you go back. Yeah, you waste time to do it, but at least you get a warning. But don't take it personally, and when I point out something that to you individually may seem trivial, it's like, who does he think he's talking to? I'm not trying to insult anybody, but I've noticed these mistakes happen again and again. The zero force members concept. The idea is that this is a general principle. It doesn't have to be a zero force member that you identify, but the general principle is if a set of forces concurrent at a hinged joint, so this is a requirement. It has to be a hinged joint. It can't be a rigid joint. In other words, there can't be more moments and stuff like that acting. So a set of forces concurrent at a hinged joint are such that when grouped into lines of action, I'm probably being too wordy about this. When grouped, have only two lines of action. What I mean by that is, let's say you have a force like this, and a force like this, and a force like this acting at a particular joint, right? Now you have, here is a line of action. Here is another line of action. And here is a third line of action, right? So when I draw those lines of action, there may be more than one on a particular line, but those lines of action, there are three. This principle would not apply to this particular situation. However, if you have, like, that truss, for example, there was a node that looked like this, didn't it? There was a node that looked like that, and there was a member force here and a force here and so on. Not a member force, an applied force. If you looked at that joint now, that would be a hinged joint. There are four member forces coming to, actually there are four forces coming together there. There is one member force. We will assume that it is tension. So if we draw the free body diagram of that, we will call that some force, F1. Another member force, we'll call it F2. Another member force, we'll call it F3. And then you have the 40 kip load, right? So there are four forces, of which three are member forces. One is an externally applied force. Your lines of action, if you draw them, are this one and this one. Now, so this would be a situation where this is still a hanging sentence. I have started with the F and there's a comma, so I still have something else to write. But this situation would apply to this particular, or rather, this principle I'm about to write would apply to this particular situation. So what can we say? And by the way, this angle does not have to be 90 degrees. This would have been okay even if the member forces, or rather, even if the forces were organized like this. There also, you would have two lines of action, one being this and one being that. So the angle doesn't have to be 90 degrees. What has to be true is there has to be only two lines of action for all the forces. Then, if that is true, then we can say the following. Number one, any force by itself, a solitary force on its line of action, must be a zero force member. And number two is any solitary pair, in other words, nothing else but the pair. Okay? Nothing else but the pair must be equal and opposite. Now, if you were given a truss and you're asked a question about a particular member force, and if this examination gave you the answer to be either zero or something, for example, here we can say two things for this particular node. We can say that F1 and F2 must be equal and opposite, because that's a solitary pair, right? F1 and F2 must be equal and opposite. Similarly, F3 and 40 must be equal and opposite. So, since one is known, 40, F3 must be exactly equal to 40 kips. And because this 40 kips is pulling away from the joint, F3 also has to be pulling away on the joint for it to be in equilibrium, which means it is tension. So to solve that member force, F3, this one, we did not have to solve for reactions or none of that usual stuff that we think must happen first. So sometimes when we get into the practice, and sometimes when we do too much practice, is we get into this rhythm of when we are given a truss, this is what I do first, this is what I do second, this is what I do third. However, on this exam, you got to sort of retrain yourself to do just the minimum amount of work needed to answer that question. Know what I mean? For example, there may be a question, I'm not necessarily saying structural, but there may be a question where you can go down 4 or 5 steps of calculations and calculate this, that, and the other. And there's a real danger if you just get into the flow of things saying, this is what I do, this is what I'm going to do, right? It's quite possible that you had your answer to their question, the question that they asked at the end of the second line of calculations. And you kept on going because you forgot or you didn't pay enough attention to what precisely the question was, right? All that time is wasted. Steps 3, 4, and 5 are wasted because you could have stopped. So they're not asking you to solve everything. They're asking you to answer a specific question, which is, even though it sounds kind of weird, it's like, how could you lose sight of that because you're answering these questions? Is sometimes we do. Sometimes we just get in the flow and start doing stuff, but we already had our answer like 5 minutes ago. So those are generic things. Those can affect not only a structural question, but a question from anywhere. And that kind of thing you can weed out of your system the more practice you do. So hopefully, as you go through the next 2.5 months, as you work on more and more problems, um, you will probably notice yourself making less and less of these things, these mistakes or oversights or whatever you want to call them. Sometimes they're not even mistakes, they're just you're doing extra work. All right, another type of question. Are we on trusses, do we need to I believe one of the NCS sample questions looked just like this. It looked like this. Well, actually, this was interesting because, or maybe not even like this. Oh, maybe, okay, let's do it this way. This is what it was. It was a cantilever truss, and it was supported, it was like this. There were loads here, 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 and so on. This is not precisely it, but you'll notice that in this particular case, if they ask you for a member force, you don't need the support reactions, right? This is like that cantilever truss that I drew, because you can just take a cut anywhere that's appropriate to finding that particular answer, and you can solve the right side of the structure, which does not involve the reactions. Okay, what was the question? What was the answer to the first truss problem? Find force EF. Let's go back. Force EF. Oh, is this the one? The F3, right? F3 is what we called EF. So if you solve this, you've got, what is it? F3, take that on the other side, 1200 minus 600, 600 plus 200, 800. So F3 will be 80 kips. It'll turn out positive from this calculation, so that means your interpretation is F3 is 80 kips tension. F3 was the EF member. I just wrote them as F1, F2, F3 here. Okay, I just didn't complete the solution, but basically saying that if you get to this point quickly, then great, because you're not dealing with any simultaneous equations or anything like that. You can just get a solution direct straight out of that one. Did I answer it? You're okay? All right. So in this one, notice that the only node at which that condition that I talked about, 2 lines of action only, there are 2 nodes where that is true. One is this node, where there is a horizontal member and there is a vertical member and a vertical force. So all the forces at this node are organized in 2 lines of action. So we can right away say that this member force is a zero force member. We can say this must be a zero force member. Weird as it may sound. So basically the structure is functioning as if there is a load hanging from here. And these two must be equal and opposite. So if this member force were, let's say, 25 kips, the force in this one would be 25 kips tension, because it would have to pull away to match this 25 pulling down. Right? So we can say this is a zero force member. And the only other one where the condition exists is this node, where you have a vertical member, a horizontal member, a vertical reaction, and a horizontal reaction, the 2 reaction forces at the pin. The four forces altogether are all organized in two lines of action. So whatever this member force is, this horizontal one, will be equal and opposite to whatever the member reaction is, or the structure reaction is here, horizontal. And same thing for this other pair. But because they're in pairs, I can't say that either one is a zero force member, right? So I can only say that they occur in pairs. But here I can at least say that one. Sometimes making this a zero force member may simplify the next joint over. So if you look at the next joint over, I have a vertical force and a vertical force. That's one line of action. I have a horizontal force and used to be a horizontal force here, but that went away. So there's only one horizontal force there. And then I have a diagonal force there, right? Now, I don't have two lines of action. I have three. I have a vertical, I have a horizontal, I have one on an angle. So that simplified condition doesn't exist, so I can't say anything. And the same is true for the others. Another thing that you could probably say fairly easily here, sometimes it's a matter of habit, is how easily you spot certain things. It's a matter of habit. It's like I'm not necessarily saying that these are the scenarios that will show up at your exam, but I'm saying that if you now look at this joint, right, this joint is also a little bit unique in that there are three member forces that are in equilibrium at that joint. Three, one of them being horizontal, one of them is vertical, and one of them is diagonal. So if you remember your Pythagoras' theorem, basically it has to be true that if this force is a 25 kip, and let's just for argument's sake, let's say that these panels are 30 feet and the height is, let's say, 12 feet. Okay, so now if you look at that force triangle right there formed by these three forces, you have a horizontal, which is 30, and a vertical, which is 12. So this drawing is not to scale, but that's a force triangle that will form, right? It'll form similar to the geometric triangle, which is 12 high and 30 long horizontally. So 12 is to 30. If I simplify by 6, that'll be 2 is to 5. That means this will be square root of 29, right? 5 squared plus 2 squared, 29, square root of 29. Which means that my forces are also going to be in the same proportion. So in other words, if the vertical proportion is 2 and the horizontal proportion is 5, that's a factor of 2.5. That means if this is 25, if the vertical is 25, this will be 5 over 2, 2.5 times 25, or 62.5. You can say that just by inspection without writing down equations and so on. And therefore, by necessity, this force will have to be one coming in, because you notice that what happens with these two, they push inwards, tensile, and the compressive effect on the member has to keep it in equilibrium. And this must be square root of 29 over 2 multiplied by 25, whatever that is. I can't do that in my head. Do you notice then that this force and this force and this force, whatever it turns out to be, I don't like keeping things hanging. 29 square root divided by 2 times 25 is 67.3. What? This turned out then to be 67.3. Those proportions 25, 62.5. Oh, and should be on the other diagonal. And 67.3. They follow the same proportions as 2, 5, and square root of 29. And this is true. So sometimes when three forces, only three forces meet at a hinged joint, and two of them are horizontal and vertical, a visual solution visual solution is possible without writing out equations. Well, shortcuts are like this. A shortcut is only good if it leads you to the right answer. So when I suggest a shortcut, I'm suggesting something because it is something that I am comfortable with, right? Because it's something I do. But that doesn't mean that you have to do it by the shortcut method in spite of being uncomfortable with it. It's like you're not getting it right consistently every single time, but in that case, you're better off doing it the traditional approach, writing out equations and maybe taking 2 or 3 minutes extra, but getting it right. So every single shortcut, whether I suggest it or anybody else suggests it, is you've got to test it out. If you're not comfortable with it, in spite of trying it a few times, and a shortcut has to be visible, meaning you have to be able to see that there could be a shortcut here, right? And that comes from familiarity and so on, and use and so on. If you work in a particular industry, and then you work with a rule of thumb that works like 95% of time, and I'm not even aware of it, then I won't see it in a particular scenario. I won't even recognize that I could use that rule of thumb to get a very quick shot on one of the answers, but you might see it. Similarly, I'm suggesting a shortcut here, but that's not to say that you must solve it that way. But I'm just saying that when this situation arises, there may be a shortcut to solve it instead of going through the laborious writing out of equations, drawing free body diagrams, and this and that. Okay, so definitely I would put the truss analysis for truss member forces, I would put that high up on the list, because very rarely have I heard that there was a full 8 structure, or 7, whatever it is, 7 structural mechanics courses, and none of that was dealing with trusses or anything like that. Technically, actually, if you look at the syllabus, you'll see that there are, in category 4, structural mechanics says 6 questions. That's what we're talking about now. And category 7 is materials. And in that materials category, about half is geotech and about half is structural mechanics of materials or material science, material properties and that kind of stuff. So I would say out of the 6 questions there, 3 out of 6 questions are structural, relate to like steel, concrete, typical, or maybe 2 out of 3, maybe 3 out of 6 relate to the structural area or mechanics of materials. So when you talk about mechanics of materials, we'll talk about this. So really we are covering, in our AM discussion, we are covering about 9 questions out of the 40 in the morning. All right. Another thing that is high on that list, and that is shear and moment diagrams. There are 2 kinds of questions that they typically ask. One is qualitative. In other words, identify the correct shape. Of a shear or a moment diagram. And the number 2 is quantitative, where they ask you for a value of shear, or bending moment at a specific spot at a certain point, or the maximum shear or bending moment in the beam. Now, this question, the value of the bending moment or shear at a particular point, doesn't require you to really draw the entire shear moment diagram. The other two actually require you to understand how to draw the shear and moment diagrams, because on the one, you're not dealing with any numbers, but you're trying to identify the one that could be the correct shape. All the other three will have violations, will violate some rule or the other. So the question is, what are those rules? What are those rules? And for this one, you would, because they're asking for a maximum value, by default, looking at the structure, maybe you don't know where the maximum shear or the maximum moment would occur. So unless you draw the entire diagram, you don't really know which is the maximum value, right? So for this one, you'd have to draw the diagram fully. So let's say let's start with, let's say you have a beam with a overhangs actually, and let's say there is a point load on each overhang. There's a distributed load here. Now, first of all, there are zones for this beam. Well, let's start back. There are points at which changes in loading occur. This would be such a point. Obviously, the beginning and the ending point of the structure would always be key points. And then between there and the first support, no change occurs. So the first support is where some kind of change occurs. A reaction force comes into play. Then this point would be another point where some change occurs. A new distributed load comes into play. But the nature of the distributed load stays the same until you hit this point where a roller brings in a new force, a reaction into play, and then you have the end of the structure. So there are 5 key points for this particular structure. So there are 4 zones altogether. So there is a zone here, and one here, and one here, and one here. Now within each one of those zones, notice that the yellow markings I did, if I was not careful, I guess I was a little careful. Notice that the yellow zones exclude the points at which the changes occur. So these are considered like discontinuity points. But within this zone, wouldn't you say that the distributed load was 0? This is the distributed load acting on the structure, right? The point load is a discontinuity. It occurs all at once at a point. But if I were to look at just after the point load and just before the support, in that zone, there is no distributed load. Same is true for this one, and the same is true for this last one. So for all 3 of these, we would say that the distributed load is 0. But for this one, we would say that the distributed load is a constant, right? Whatever that value is. Now, dv dx is minus w, w being the distributed load, v being the shear. So the derivative of the shear is equal to the distributed load. Right? Another way of looking at it is the shear is basically the integral of the w. So whenever you have a load function that is 0, you integrate it, your shear function will be a constant. Different constants, C1, C2, etc., but shear will be a constant. But then if your load function is a constant, you integrate C, you get Cx plus D, right? So the shear function here will be linear. So we know, okay, better not tempt Murphy. I'm going to save this in case. I didn't even make space for it. Just save it. All right. So the point is that if they asked you to identify a shear, if they asked you to identify a shear diagram, you expect a diagram that is, if I draw these lines straight down here, you expect your shear diagram to be a constant, and then constant, constant, linear, something like that. A shear diagram like this will not break any of the rules that we have come up from looking at the nature of the loading, that the shear must be a constant, 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 and linear in these zones 1, 2, 4, and 3, the order in which I said them. So if you see a choice, one of the choices showing that the second zone shows a linear shear diagram, just that is enough to disqualify that particular choice, right? And if a particular choice is disqualified, don't waste any more time in looking at the rest of that choice because it's already been disqualified. Okay, then move on to the next one. So elimination is a great strategy for these problems. Use elimination to arrive at the answer, at the one answer that shows no discrepancies. And then the other relationship is dm dx is equal to v. Now sometimes people get these mixed up, especially if this is not something that they do day in and day out, and they did it way back in college in a junior level course or whatever. Now if you look at units, you could never have something like dv dx is equal to, or rather dm dx is equal to minus w. This could never be true. If you look at the units, the moment has units of force times length, and x is length. What this would give you is, it would give you a force. dm dx will give you a force, dimensionally speaking. This is not a force, this is a force density, force per unit length. So it doesn't match. So this could never be right. But here you've got a force times length divided by length that will give you a force which matches the force on the right side. Okay, this part is actually fairly well summarized in the FE handbook too. So here the corresponding equation would be m is the integral of the shear diagram. So that means if your shears were constant, constant, linear, constant, right? If your shears were these, then you know that your moments must be linear, linear, quadratic, and linear. By integrating these, right? So your moment diagram may look like, I mean, this wouldn't break any rules if it were to look like linear, linear, something like that. This portion, okay, man, this thing is misbehaving. When we take a break, nobody likes listening to my voice, including myself, for 3 hours straight. So we typically take a break at like midpoint. So when you take a break, I'm going to get out of this file and get back in again because it's misbehaving a little bit. Notice that this portion where the shear diagram is straight, the corresponding portion of the bending moment diagram is quadratic. I have it a little, it doesn't quite match the edges. But this quadratic, this curve, x squared, must match in extent this particular section of the beam where the shear is linear. And the maximum moment must correspond to the zero crossing of the shear. So any choice, let's say they give you a choice that what is a correct bending moment diagram, any one that violates one of these rules is basically out. Just one violation and it's out. Okay. All right. So let's take one with just numerical values. Boy. Hang on, I'm just waiting for, hopefully the save will take away the tablet. Usually is perfectly fine. I loved Windows 7 and then I got kind of forced into upgrading everything to Windows 10. I'm not sure I can say the same for Windows 10. I'm just waiting for this file save to complete so I can. All right, so if there is a if there is a why do you do this to me? Okay, let me get out and get back in. If there is a numerical problem where they give you a beam with specific loading numbers and so on, and they ask you what is the maximum shear or maximum bending moment on that beam, they're not going to get into the AM questions are not going to get into moving loads. Okay, the load types in the AM questions, they don't mention moving loads. In the PM section, they do mention moving loads, so you have to understand some of the basics of influence lines and things like that for moving loads. Transient loads especially, how to place the live loading to produce the maximum effect. AM questions are not going to get into that. So if the loading is specified, then it is what it is. It's what's as it is shown. And then for that loading, you typically will have to, if they're asking for a numerical value, like what is the maximum bending moment for this particular beam, then you have to calculate the reactions and then start from there. This is getting annoying. Not a sometimes you just feel like all right. Okay, hopefully I did a save just before that happened, so hopefully didn't lose anything. Okay. Good. All right, so if you have, let's say, something like that, say these are like 8 feet, 10 feet, 8 feet, 6 kips per foot, and let's say 20 kips. So the first step would be to figure out the reactions, of course. For calculating reactions, it's acceptable to lump this as its resultant. So that would be a 48 kip resultant exactly at the middle, uniformly distributed load. So exactly in the middle. For triangular, you know that the resultant force in a triangular load pattern would be half base times height. For a rectangle, base times height, but the centroid of the triangle would be at 1/3 of the base. Come on. One-third of the base and 2/3 of the base here. So when you use that lumping concept, you lump that entire distributed load into a single resultant as a point load, so you can take moments. Make sure to position it at the centroid of the load. And for this is about as complex as the PE exam will get. I don't think they'll give you anything more than a linearly varying distributed load. If you have a trapezoid, you can probably the easiest way to do that would be to break it up into a rectangular load with resultant at the center and a triangular portion with resultant at its center or its centroid, and deal with it as two separate loads instead of dealing with the entire trapezoid, because the definition for the centroid of a trapezoid is kind of weird, and it's of the form that lends itself to mistakes. So it's much better to break it up into two separate ones. Here, so if I take moments about A, um, stick to clockwise positive for no particular reason, and then I have 20 times 8 plus 48 times, what is that, 18 and 4, 22, minus by times 26 is equal to 0, right? Um, I'm writing this out, but you notice that if you get really used to it, because rarely on the PE exam do they get too exotic with loadings and structure and the type of structures and so on. So if you're dealing with something like this, and if you say, well, I'm trying to take moments about A so that I can figure out the vertical reaction at D or B, and this is By, and I can see that about A, By would turn counterclockwise. So what it's doing is its moment is countering all the clockwise moments. So if I could take all my clockwise moments, and if I could divide them by that arm from A to B, which is 26 feet, it should give me my force By. This you can do straight in your calculator if you see it that way. So you can just pull up, you can just say, why does it, God. So then you can say, well, I have a 20 times 8, that's clockwise. So I'm going to leave it as positive. Then I have a 48 times 22, That's clockwise. And then all that moment has to be resisted by 26 times by. So if I divide that by 26, I'll get by. So that became 1216 divided by 26 is 49.3 kips. 49.8 kips actually. Okay, this approach allows you to do it directly in your calculator instead of writing this out, and obviously is faster. Once again, do it this way, the second way, only if you are comfortable and you've done it like 10 times in a row and you've never made a mistake in those 10 times, then I think you're all set with it. But if you find that when you try to do it that way, you may be saving yourself 30 seconds, but you are not always consistent, then you're better off doing this, because it's not hugely demanding what we're doing here to write it out. It's just have to write it out. Know what I mean? If in this summation of clockwise moments, if you came across one that was counterclockwise, for example, if there was a overhang here and there was a load here, you just take it into the sum as a negative. You would not exclude it, you would include it, but as a negative. Okay? So now we have our reaction, and we know that our total load is 68, so the other one must be 18.2. So we know both our reactions. So we have a 18.2 here, and we have a 49.8 here, right? So we know that our shear diagram, this is something that helps you line up the appropriate sections with the loads. So it'll go up 18.2. So for the shear diagram, simply follow the load, track the load as they are. The shear diagram is tracking these kind of forces, right? This is your shear. So anytime you see any kinds of forces like that, like this reaction, 18.2 will push the shear diagram up 18.2. Then there is nothing happening, so the shear diagram will also stay the same. Then you have a 20 down, which pushes the shear diagram down by 20, and that'll come up to minus 1.8. And then nothing happens, so this diagram stays flat. And then you have a total load of 48 here. Now, from here to here, in other words, x equal to 18 to x equal to 26, that third segment of the beam, the load appears uniformly, so the shear diagram must also change uniformly. So a total change of 48 will get it from negative 1.8 to negative 49.8. So that's your shear diagram. Notice right away that your bending moment maximum will occur at that point because of that rule of maxima and minima. If dm dx is equal to v, then when m is a maximum or a minimum, v goes through a zero crossing. The gradient, the slope must be zero, which means dm dx must be zero, which means shear must be zero. So the zero crossing for the shear is your indication of where the maximum moment must be. So in that case, you don't really need, if the question was here, what is the maximum bending moment value? There are two ways to arrive at this point. One is from the left through this shape, or from the right through these two shapes. Now, obviously, the first option is easier because not only is it only a single shape that you have to go through, you also have a shape that is easy, a rectangle. Here, not only you have a rectangle, but you have a trapezoid. So that means all you have to do is you have to figure out the area of this particular shape. I did something wrong somewhere. This doesn't look right. 18.2 times 8 is going to give you like 150-ish or thereabouts, 147. And that's going to be from 0 to that value 147. Does that look right? That doesn't look right at all. This shape is much bigger. basically your general, if this were the shear diagram, it would rise because of the positive area, then fall by that area, by that negative area, and then fall some more as a parabola. So x to the power 1, these are both linear, but this last segment is parabolic, and it would fall back to 0 because that end is a pinned end. So the bending moment must be equal to 0 at both of these ends, right? But for it to do that, the positive area must be equal to the sum of the total negative area, which doesn't look like the case here. So I messed up somewhere. Maybe in going from the total load was 68, this turned out to be 49.8, so that would be 18.2. That seems right. Maybe here. 20, come on, 20 times 8 plus 48 times 22. 46.8, and I wrote it up there as 49.8. That's where I, okay. So this is should be 49.8. Instead of that, should be 46.8. So that'll be 21.2. Yeah, that'll make the slight changes. Sorry about that. Okay, so that'll make the positive area. My point is that now that we know that this is 21.2, we can very quickly arrive at what that rectangular area is on the left. And that value will be, this area will be 21.2 multiplied by 8, or 169.6, almost 170. So it's going to rise to 169.6 and then start falling away. Oh wait, no. Gah. Okay. So we have a 21.2. 8 feet away we have a 20. Then 6 feet away we have a distributed load containing a total load of 48. And then we have 46.8. Your shear diagram will actually not go through a zero crossing there, so it makes it a little bit harder. 21.2 will then drop down to 1.2 here because of the 20 load. Stay like that. Actually, I'm kind of glad that that happened. Now, this is a little bit harder than what happened earlier. What happened earlier was it went through a zero crossing right at that location of that 20 kip load. And so we ended up with a nice rectangle here and a rectangle here. Here, we have a rectangle here and a rectangle here. So you got three shapes, actually 4 shapes. You got a rectangle here, positive. You have a rectangle here, positive. Then you have a tiny little triangle here, positive. And then you've got a triangle here, much bigger, which is negative. So obviously, those 3 positive areas must add up to be equal to that 1 negative area, right? Now, we know that the maximum bending moment will occur here, point of zero crossing, therefore, location of maximum bending moment. So that means our bending moment diagram will look kind of like, it'll be over that last section, it'll be a parabola with a maximum here, so it'll look kind of like that. I'm exaggerating because that's so tiny, it's probably not enough to make that much of a change. But anyway, it's going to be a parabolic section that looks like that. Maximum will correspond to that zero crossing point. And then it's rising. So it's rising slowly here and rapidly here. I didn't draw it to scale to make much of a distinction, but this rises quickly and then rather flat, and then the parabola, right? So we know that this area is 169.6, 21.2 times 8. So we know this value is 169.6. Then we know this little piece is 1.2 times 6, I think it was, right? So this area is 7.2. I'm going to circle these areas because the areas are actually 21.2 kips times 8 feet. So this is kip foot. That's why we're using these areas to figure out your moments, which are kip foot. So 170 and another 7. So this will be like 177 or so. It's going to rise a tad higher than that. Now, depending on your answer choices, the correct answer in this case, correct answer for maximum bending moment is slightly more than 177. Only if you have two choices, two or more choices that fit that category, is the next step warranted. And that is precisely how much is it? Remember, it's a multiple choice exam, right? In a multiple choice exam, you're asked to pick one of the answers, not come up with the answer yourself. So if you see that there is only one that is like 177.5 or something, everything else is either lower or much higher, then there's no point in working out what the exact answer is. But if you had to, the best way to look at that is to focus on this triangle and to say that it drops down from 1.2 kips at a slope of, I think it was 6 kips per foot, right? So that little triangle, that little blue triangle, is dropping down from 1.2 kips at a slope at the rate of 6 kips per foot. So if you use the rise over run concept, right? Rise, this is the rise, this is the run, and this is the slope, then this must be 0.2 feet. Isn't that right? So I'm going to mark this blue. That is what we're looking at, that little piece over there. But 1.2 kips divided by 6 kips per foot should give you the distance. And look at the units, they correspond, 0.2 feet. And so then you can calculate the area of that as 1/2 0.2 times 1.2. So that area then, area of the blue portion is half base times height. Base is 0.2 feet times 1.2 kips. So that will be 0.12 kip foot. So that means if this is 177, this will be 177.1. Okay. So in this particular case, you had to work up at least up to this diagram, up to the shear diagram, to be able to answer what your maximum bending moment is, because until you get to the shear diagram fully, you don't know what the zero crossing point is for the shear, and therefore you don't know up to which to calculate the areas. The fact that these areas add up to your bending moment diagram comes from that same one we were talking about, dm dx is equal to v. So the integral form of that is change in delta m is like the integral of v dx, which basically says that change in bending moment from one section to another is equal to the area under the shear diagram between the two sections. So we are building the moment diagram by accumulating areas from the shear diagram, right? We're starting at a 0, We are saying we first accumulate the yellow area. And so then we go from 0 to 169.6. Then we accumulate the green area. Then we go from 169.6 to 176.8 or something. And so on, right? We keep accumulating positive areas until we hit that point, and then the negative area brings us back down. And that's why when we were doing it before and I had the number wrong, if the areas don't bring you back to 0, that means that equilibrium, which says summation of moments is equal to 0, was not satisfied. Right? I had the wrong numbers, so equilibrium was not satisfied. All right, so that's the other thing I would say is something to do with shear moment diagrams, whether qualitative or quantitative, is almost a certainty. Right. Should we take a little break here, like 5 minutes or so? If you guys have anything, I mean, I have done the course for many years, but then every single audience is different. If anybody feels there is something I should do differently, then I don't absolutely mind. Feel free to let me know anything I can change. Um, so you can let me know that through email after, or you can let me know through the chat window now. But let's take a little 5-minute breather and I'll be right back. All right, I'm back. Okay, so get away from calculating moments and shears and axial forces and all that, and then now, so we are talking about, let's say, on a particular beam, you have a bunch of forces acting. So there's a 10 kip force at a 1:1 slope, and there's a vertical force, the 20 kips, and these are, just say, 4 feet, 8 feet, and 8 feet. So if you look at the free body diagram of this, we can say that I have a 1:1 means your square root of 2, which means at this point you really have a 7.07 and a 7.07 component. And so this reaction is, by inspection, 7.07, and then you do your moments, 7.07 times 4 clockwise, and a 20 times the whole 12. I'm taking moments about A, plus 20 times 12. That entire clockwise moment has got to be resisted by the reaction here, which is at a distance of 20 feet. So divide that by 20. That gives you the reaction there as 13.41. And the reaction here from Fy is, total is 27.07. So that subtracted from 27.07 is 13.66. So that's your free body diagram solved from a external point of view. In other words, you figured out what the external reactions are and so on. Now, if I ask the question, what kind of what stresses exists at x equal to, let's say, 10 feet, right? Which would be about here, midpoint, midspan. Now, if I were to make a cut at midspan, and if I were to say that, well, I'm looking at, let's say, the left side, doesn't have to be, but let's say I'm looking at the left side, and I can put in my components like that, right? So these are all my external forces and external reactions acting on that section of the beam, that half of the beam, because I'm looking at the free body diagram of that portion to expose what's going on at midspan. So at midspan, you have a normal force, which is typically written like that. You have a shear force, which is typically written like that. How you represent your shear and moments at a particular cut depends on a adopted sign convention. So the adopted sign convention that is most common. Not that you could not go against the grain. You could do something different. But what you'll see in most places is tension positive, which we have encountered elsewhere. Shear, this is considered positive shear. Any kind of shear that pushes the left side up and the right side down. And consistent with that is this is considered positive moment, what acts like that on a portion of the beam. So the three unknown internal loads, not forces because one of them is a moment, the internal loads at that cut section will be represented like this. Now, if I were to keep the right side of the beam, I would put them in exactly opposite, right? The right side of the beam with a cut there, that same place, would have the 13.41 on it, the reaction on the right, and then I would put in the normal like that, the shear like that, and the moment like that. So it's best to, if you think that you might get these mixed up, it's best to always do it one way. In other words, always be consistent and say, this is my way, this is how I do it. And so that way you will not flip-flop. Now, in order to figure out these stresses, internal stresses, we need to figure out what the moment is, we need to figure out normal forces, and so on. So if I look at summation of forces in the x direction for this substructure, I see there is a negative 7.07, there's a positive 7.07, and there is n. That obviously means that n is 0. By the time we get to n, the axial forces have balanced out, and so there's nothing left over at n. So n is 0. So there is no normal force. But if I do summation of Fy equal to 0, I'll see 13.66 positive upwards, negative 7.07 minus V is equal to 0. That'll tell me V is equal to 6.59. Turns out positive. So that means that at that location we have positive shear, which means it's shear of this kind. And if I take summation of moments about where the cut is, and if I stick to clockwise positive, in other words, this is where the cut is, take moments about that point, then I will get minus m, because the m that I've put in there is a counterclockwise moment. So if my convention here, you got to make sure that you understand that the convention of putting in these is not the same as the convention I adopt here for what I call positive, clockwise positive, counterclockwise positive. Okay, they're not connected and they're not the same. So I can flip-flop, but whatever I write here has to be consistent with what shows up here. So minus m, because it's counterclockwise, and then what else? The n and the v, the advantage of taking moments about the cut is I don't have to deal with n and the v, and I can say 7.07 times, that was at a distance of 6 feet from where I am at the cut, 6 feet from here to that location of that force, and then the 13.66 times 10 feet, and that one's positive, right? So as far as this moment equation is concerned, taking moments about that center of that cut, the 7.07 and 7.07, these two are collinear with that, so they don't matter. So the only ones, again, if you take an inventory, you won't miss anything. In other words, you look at it and you say, the only ones that I need to take moments of are this 7.07 over here, and this 13.66 over here, and of course, the couple that exists right there. Those are the three terms that should be in your equation, and those are the three terms that are here. Is equal to 0, and that will give you m is equal to 136 minus 42 minus 42.4. Yeah, 94.2. And it turns out to be positive. Okay, so now if you have to talk about stresses, you have to know what the cross-section looks like. So the next thing is, what is the need to know the cross-section to translate these internal forces into stresses, right? Large section, small stress, and so on. So I need to know, so far I've represented that beam as a stick figure. I haven't said anything about what the cross section is. So let's just say, let's say it's a rectangular cross section. It's rectangular. Let's say it looks like 12 inches wide and 20 inches deep. Okay, it may be oversized. I'm just arbitrarily choosing a size. It may be oversized for the purpose. We'll see. So that means that at that particular location, what you have is, at that location, you have no normal force. Normal force was 0. You have a shear force of 6.59 kips. And you have a bending moment of 94.2 kip foot. So the normal force is 0, but if it was there, it's a pretty simple normal force. The normal force N would have caused a normal stress N divided by the cross-sectional area. Right, so you just take the cross-sectional area and assume that that normal force is acting exactly concentric at the centroid, so we will assume it's a uniform distribution over the entire area. But in this case, it had a value of 0, so we don't have to do that. The bending moment, on the other hand, the M equal to 94.2 kip foot. In fact, my cross-section, this is where this mistake is common, is getting units mixed up, inches and feet. Typically, your moments will be in kip foot to keep the number small, and typically your cross-sectional dimensions will be given in inches, so make sure that you adjust. The easiest thing to do would be to convert the moment right here to kip inch. 94.2, I think it was, I messed up the number, times 12 is 1130 kip inch. So that moment, if you forget anything else, if I look at this picture and if I look at that moment, obviously it will produce a pattern of compression on the top face or the top edge and tension on the bottom edge. It will do something like, here's your centroid. It will produce a maximum compression at the top, maximum tension at the bottom, and it'll be a linear transition between the two, right? So we typically show that in a side face view, we show that as like that. And that bending stress formula is my over I. Including a negative sign helps you interpret what kind of sign it is. We'll talk about that. The maximum bending stress, which typically is what you're interested in, not the stress anywhere, but the stress at the maximum point, whether it be the compression or the tension, if you're interested in that, the maximum bending stress will obviously be M times wherever the Y is maximum, in other words, the furthest out point, which for a rectangle, Y max, Y to the top, and Y to the bottom are the same. But for an asymmetric section, they would not be. Divided by I. This can also be written as M divided by the section modulus S. So S is the elastic section modulus. Now for a rectangle, it's worthwhile remembering, for a rectangle, B times H, the moment of inertia about this axis, call that the x-axis, the moment of inertia about the x-axis is 1/12 base times height cubed, and the section modulus is 1/6 base times height squared. So in this case, if you were interested in finding the maximum stress, in this case, If you wanted to use that formula, your section modulus would be, or rather your maximum bending stress would be 1130 kip inch divided by 1/6. I said 12 and 20, right? 12 times 20 squared times 6 divided by 12 divided by 20 squared is 1.41 KSI. Kips per square inch. And that would be the same top and bottom. And the shear distribution, the shear force V was 6.59 or something. Yeah, 6.59. Now the calculating shear stress is a little messy because the formula for shear stress due to a transverse shear force is this: VQ over IB. To calculate this, you need the shear force, which we know, which we have, the moment of inertia, which we can calculate for a rectangle pretty easily. B is the width of the section where you are calculating the shear stress. So for a rectangle, the width is constant. Throughout its depth, it's wide, it's 12 inches wide. So that would be just by observation. This takes some work, and this actually then gives you the calculation of the shear stress. But there is, for a rectangle, again, specifically for a rectangle, singling out because not only because this is a rectangle, but also because the rectangle can be a fairly commonly used cross-section for timber and concrete, especially, not for steel. And so it's worthwhile knowing that the maximum shear stress is given by 3 over 2 V divided by BH. This is certainly a much easier calculation than doing from the generic. If you apply this generic formula to the rectangle, this is what you get, right? So in our case, that would be 3 over 2, 6.59 kips divided by 12 times 20, and that would be 6.59 times 1.5 divided by 240, tiny, 0.041 KSI. So 41 PSI and 1410 PSI. Okay, so remember that these formulas are specific to rectangles, not to any other shape. The generic formula for any shape is this one and this one. However, with steel, the wide flange shapes are very common, right? So if you have, for a steel section, the wide flange shapes are very commonly used for beams. And it could be that when you, just like we did for the rectangular beam, when you cut or you looked at a particular location of this beam, you found a shear force of 6.59 and a bending moment of whatever it was. And you have the same situation where the cross section is now a wide flange shape. Now the distribution of bending stress is very similar to what we had before. It's 0 at the neutral axis, and then it pivots linear about the neutral axis. So we know that if it's a symmetric wide flange shape, the stresses of the top, the maximum stress at the top, compression, and the maximum stress at the bottom, tension, will be the same in magnitude, right? And it'll be the same linear variation. It's just not so hard to calculate. The shear stress distribution, if you apply that generic formula, will look something like something like this. In the flanges, it'll have a tiny amount of shear stress, but then it'll jump because of this sudden change in width from going from here to here. It'll have a discontinuity, and then it'll show something like this, and the maximum will be at the neutral axis. So a very common approximation of this is to say, let's forget about these two little pieces over there. They're not doing hardly anything. Let's take my entire shear force and let's approximate this parabolic kind of shape with something that is rectangular. And the deeper the shape is, the better that approximation gets, which is take your V and divide it by simply the area of the web, which is also very quick. So the area of the web is basically talking about just this portion. So that's a very quick calculation. What is the answer for which one? Is that you, Kevin? Actually, when you guys sign in, I notice a couple of you are signed in with other than the name that I have for you on the form. If you could sign in with your name, that would be better. For the last question, I mean the rectangular, this is the shear stress in the rectangular shape. This is the bending stress in the rectangular shape. I'm not exactly sure when you ask what is the answer to the last question, which one do you mean? You can come on mic if you like. I mean, we were trying to figure out what stress condition exists here. And so we first got to the internal forces, the shear, the moment, and the normal. And each one, the normal stress is this formula. It's the easiest of all. The bending stress is this formula. So we got 1410 psi or 1.41 ksi for that one, for the bending stress. And the tension and compression will be equal because of the symmetry of the shape. And for shear, because it's rectangular, question was, what is the stress at 10 feet? Okay, so we are sort of breaking down all the different components of the stress. Okay, so we can't really, I mean, we'll talk about how do we talk about a single stress out of all this, but the question has to be more specific than that. What are the stresses at x equal to 10 feet? So we found that the maximum normal stress was 1.41, which either is a compression pushing in or a tension pulling out. And then the shear stress is 0.041, which is of a different nature. So we can't really add the two together. We can say, we can list sigma equal to 1.41 and tau equal to 0.041. But to combine them, we have to do something like more circles or something to combine them. This is so negligible that the other one will essentially dominate. Okay, when stresses exist, would they ask for the cumulative stress? Well, they could. I doubt it on the PE because that's more of a FE thing where they specifically want you to show, ability to manipulate or combine stresses using more circles and so on. But if you were to combine these, this is what would happen. Well, another thing you have to understand here too. Think about where the stresses are and how they combine. Here is your rectangular cross section. Here's the neutral axis. This is where the stress is. Let's just pick on the compression. This was the maximum compression at that point. Sigma compression 1.41, right? Let's call it compression. However, the shear stress distribution pattern is exactly opposite. The normal stress distribution pattern looks like this. This is sigma equal to my over I. It's got that linear variation. Tau, which is given by the VQ over IB, has a variation which looks like this. It's parabolic for a rectangular section. It's maximum here and 0 on the outside. So what do we have? Out here we have combined with sigma max, we have a tau of 0. And in here, combined with a sigma of 0, because at the neutral axis it goes through a 0, the tau is maximum of 0.041. So if we are talking about either one of those places, we don't really have to do a stress combination. At this location, the stress is all sigma. At this location, the stress is all tau, and a very small tau at that, right? However, at some intermediate location, at some intermediate point, now why would you be interested in that if it's not the maximum? I don't know, theoretically, but practically has not much value. But if I were interested in a location like that, at that point, I have some sigma and also some tau. Know what I mean? I'm looking at, do you see what I'm saying? At this level, I would be here on the bending stress, right? And I would be here on the shear stress. So I would have a non-zero sigma and a non-zero tau, and they would have to be then combined. But the taus are so small that for all practical purposes, this is the dominant thing going on for this particular cross-section. So yeah, we can talk about more circles is not.
I got it.
Yeah, got it? Okay.
Yep.
All right. More circles are not that huge for the PE, but depending on our time management, on how we manage our time today and on Thursday, we can talk about it briefly. I think there is an example in the practice problems where you're given the sigma and the tau and so on, and they are expected to be combined according to the Mohr circle theory, and then that gives you a different sigma max and a different tau max, because the point of that question was to calculate factor of safety. Actually, that's a good segue for me. The factor of safety concept. There is a predictable mistake that happens sometimes. There are two ways that a factor of safety question can be asked. One is, given an allowable, let's say an allowable stress and a desired, let me see, I want to write this just right, because if I'm trying to clarify something, I don't want to be confusing. Factor of safety in general, you would always think of it as some kind of an ultimate effect divided by the allowable or the actual effect. So it could be forces, a ratio of forces, it could be a ratio of stresses, it could be a ratio of deflections, whatever, right? This is always the limit condition. This is always the limit value or the critical value, the one up top. If your actual value is less than the limit value, obviously you're fine, right? And so the factor of safety will be greater than 1. So can you have a situation where factor of safety is less than 1? It's not desirable, but you could, right? Because we are so used to shooting for a factor of safety greater than 1, when we are dealing with numbers, there may be a mistake that we put the larger number up top and the smaller number on the bottom and get the factor of safety that way. Because we are used to, that's how it should be. But if they give you an inherently unsafe situation, right? If they give you a situation where the stabilizing forces are less than the destabilizing forces, you have an unsafe situation and your factor of safety should come out as less than 1. So always remember that the limiting value, not the larger value, but the limit value should go up top. So if you're given an allowable stress and a desired factor of safety, what was I trying to say here? No. Given let's write it differently. Given an ultimate stress given an ultimate stress and an actual stress caused by the actual loading, the factor of safety is sigma ultimate divided by sigma actual. This is the factor of safety we have. Right? It may be acceptable or unacceptable. For example, for retaining walls, the typical desired factor of safety against sliding, horizontal sliding, friction over, the whole thing about friction on the subbase and so on, is typically around 1.5 or 2, right? Now, if I have a 1.2, we have a safe situation, but not an acceptable situation because we haven't met that threshold of 1.5 or 2, whatever the code said, right? But that's what we have. Given the loads and given the capacity of the soil to resist friction below the footing of the retaining wall, that's what we have. However, if you have given a desired or target factor of safety, and an ultimate stress, because typically we know from material tests or whatever it might be, we know what the limit value is, and an ultimate stress, the allowable stress is less than or equal to ultimate divided by factor of safety. This is important, okay, because setting it equal may not allow you to move to the, remember that most nearly thing, it may not allow you to move. You will not, you will never hit the number in the answer choice dead on, right? So let's say you get a number, sigma allowable equal to 2730, and you have two choices, 2500 and 3000. You're right in the middle of them. So which one should you go to? This is important to keep track of, that your allowable stress should not exceed this value. Okay, so if your ultimate stress is, let's say, 5,000 psi and your factor of safety is 2, then you should never exceed half of 5,000 or 2,500 psi. So you should go down to the next acceptable value, even if it's not the closest. Okay, so one is a case of a factor of safety that actually exists given the loadings and so on. And the other one is, how should you adjust your loads, or what should you say about your maximum tolerable load or maximum tolerable stress based on that, and you should stay below what this gives you. So there's two different ways of looking at it. Same thing, but two different ways of looking at it. One is more of a design and one is more of an analysis. And if I were to write a very broad header to this, this is more like an analysis, analyzing what you have. And this is more design, adjusting things so that this condition is met, right? All right, so I'm glad I sort of took a sidebar into that. So for example, if you're given a, okay, let's talk about, we talked about the rectangle and it was nice and symmetric and there are some canned formulas for it. But what if they give you something like this? If they tell you that a T-shape so a beam having the T section shown is subject to the following: one, a internal normal force N equal to 18 kips at the centroid, and 2, so it's shown like that, N equal to 18 kips, and 2, a internal bending moment M equal to 50 kip foot about the centroidal axis, and that's, let's say, looks like that. Hopefully their drawing will be a little bit clearer than mine, but what I mean to draw there is that this moment is about this axis. You know, if you curl your fingers around that line, around that red line, that moment. So that produces obviously a pattern of compression up top and tension on the bottom. Hopefully you can see that, right? If you curled your fingers into about that axis, your fingers would push in near the top and pull out near the bottom. And those are, the nature of those are actually predicted if you went to the fully generic minus my over I formula, the presence of that minus. And the way we do it is we measure y positive that way from the centroid and y negative this way. And you can see there that if your bending moment, this is considered a positive bending moment, a moment that curls a shape like that. If you remember, what we're talking about is sort of a beam, and if you remember, when we made the cut on the beam, my drawing is becoming horrible. I intend to, so there's my beam, and I'm cutting it here and looking in. This type of moment was considered positive. So that type of moment is just like the moment drawn on that shape, right? So that's a positive moment. So if M is positive, when Y is positive, in other words, when you're up top, Y is positive, you'll notice that plus, and the minus will combine to give you a negative value, which means it'll predict compression up top. When Y is negative, you're down below, minus, plus, minus will give you a positive, which means it'll predict tension. So if you're interested in only the values, you don't have to include that minus sign in there. If you're interested, if you can see how the stresses will be, like by looking at it, you can visualize it, compression up top, tension on the bottom, you don't need the minus sign. But if you can't see it, the minus sign in that formula, and that entire formula, will actually predict tension or compression for you. All right, so what we need, so the question is calculate the maximum normal stress. Okay, notice I did not use the word maximum axial stress or bending stress. I said maximum normal stress. Now in this case, this will produce normal stress. And this will produce normal stress as well. So in this case, we are not talking about a normal and a shear. We're talking about two normal stresses acting the same way, or maybe, in other words, they are collinear. They can be combined. And so what we have to do is we have to see what kind of normal stress will this produce. This will produce a uniform tension everywhere, right? The N. Because the way it's shown, it's pulling out on that cross section. So it's a tension. So that N over A will produce a uniform tension everywhere. Now, if I were to combine that tension, so if I were to draw the side view of this cross section, here is the beam, the elevation view. This is the top flange right there. This is where we are cutting. And what we are saying is you have a normal stress right there. And that, presumably because it's on the neutral axis, will produce a uniform normal stress given by N over A, plus you also have, about that same axis, you have a moment that looks like that, which will produce a stress which is compression at the top and tension at the bottom. And this is the place where the two tensile stresses will combine to give you the worst case scenario, because they're both tension, so they'll add. On the top, one is a tension, one is a compression, they'll subtract. So we are looking for the stresses down here. We're looking for the stresses down here, right? On that point. So the N over A is pretty easy. Well, easy if I give you the dimensions of this cross section. So let's say this is 6 inches wide across the top, 1 inch flange, 5 inch stem, and let's say 1/2 inch wide stem right there. So 6 by 1, 5 by 1/2. Let's redraw that. You have a 6 by 1 and a 5 by 1/2. And we need to figure out where is the neutral axis. And remember, we need to figure out, to do the my over I need two things. One is the centroid location, and two is the moment of inertia. So that's basically what this problem boils down to, is figuring those two things out. After that, it's a straightforward equation. So let's take this to be our datum for everything. We'll assume y equal to 0 here. We have shape number 1 and shape number 2. Shape number 1 has an area of 5 times 0.5, 2.5 square inches, and a y of 2.5. Right? Remember, this is an area, this is an inch. Numerically, they're the same because of this 0.5, but if this was anything different, the y would still be 2.5, but the area would be different. Shape number 2 is 6 by 1, so the area is 6.0. And the y measured from the datum, this is another place where mistakes happen. You have to remember that the y must be measured consistent with this datum. So the y for that shape that we are looking for, shape number 2, is the center of that is here, which is the entire 5 plus 0.5. Right? To get from my datum to that center, I need to go through the entire stem, 5 inches, plus half of the thickness of the flange, so 5.5. So the formula for the composite average, or the weighted average for these two areas, is y1 A1 plus y2 A2 divided by A1 plus A2. Or you can write that as, if you have more than two, sorry, you'd write it as as this. So I have a 2.5 times 2.5, 6.25, plus 6 times 5.5, that's 33, divided by the total area, and that's 8.5. So 39.25 divided by 8.5 is 4.62, rounding a little. So this height, where the centroid is 4.62. That right away tells me, and this was obvious, that my total height was 1 and 5, 6 inches, right? Total height was 6 inches. This is 4.62, this must be 1.38. So I can see that my bottom edge is further from the neutral axis, obviously. If the section is top heavy, it'll pull the centroid up nearer the top, which will make the bottom edge further from the centroid, and so that's where the maximum stresses will occur. So that Y right here, that Y that we should use to calculate our stress down here must be the Y from the centroid to that location. So we have that. We have the moment, I think it was 50 kip-foot or something, and the moment of inertia is your, it's called the parallel axis theorem. We already talked about the fact that moment of inertia of the rectangle is 1/12 base times height cubed. But what we have here is if I apply this formula to either rectangle, they're both rectangles, it'll give me the moment of inertia of this rectangle about its centroid, or this rectangle about its centroid. But what I really want is I want the moment of inertia about this centroid, which is the overall centroid, right? So then the parallel axis theorem says if you've got to shift this result to a parallel axis, in other words, this gives you the result about this axis, the centroidal axis of that shape. But if I want to adjust it to the centroidal axis about any other parallel line, I use that parallel axis theorem, which is moment of inertia about the centroid plus a d squared will give you the moment of inertia about any other parallel axis. So that means that shape number 1 will give me 1/12 times 6 times 1 cubed from this formula. Sorry, that's shape number 2. Let's do it in order. Just do in case you're going over this later, no confusion. Shape number 1, the bottom one, will be 0.5 will be considered the base, because the base in that formula, base is always the edge parallel to the axis. And H is the edge perpendicular to the axis. So my axis about which the moment is right here, so this will be considered B. So 0.5 times 5 cubed, that'll be this formula right here. But it needs an adjustment, area 2.5 times D. The D will be the shift between what this turned out to be and what this was. So it'll be 4.62 minus 2.5 squared. That is the parallel shift between the local axis and the overall or the global axis, right? Similarly, for the other one, 1/12, now this time 6 will be considered the base and 1 will be considered the height, plus area is 6 multiplied by its local is 5.5 and the global is 4.62. Notice that getting these flip-flop, meaning writing it as 2.5, local minus global versus global minus local doesn't matter because it's d squared. Okay, so all you need is the shift and that square it. So if we do all this, we'll get a moment of inertia, which is 0.5 divided by 12 times 5 cubed plus 2.5 times 4.62 minus 2.5 squared plus 6 divided by 12 plus 6 times 5.5 minus 4.62 squared. 21.59, pretty small. So again, and this will be in inches to the power 4. Both of these formulas, they're inches to the power 4. AD squared is length squared times length squared, inches to the fourth. Anyway, a pretty small number. Hopefully I didn't mess up anywhere. Now I'm thinking of, so the stresses will be pretty large, I think. So at the bottom edge, the bending stress will be equal to the moment, I think I said 50 kip foot. The moment is 50 kip foot, which is 600 kip inch. So it'll be 600 my. 4.62 was the y, and 21.59, right? 21.59 is the I. Huge. 600 times 4.62 divided by 21.59 is 128 KSI. And this is tensile. This is the bending stress. And the axial stress, which is the N over A, was 18 kips divided by, I think the total area was 8.5 square inches, right? 6 and 2.5. Oops. So that's 18 divided by 8.5 is 2.12 kips per square inch. And this is also tensile, and this is uniform tensile. This is varying. This is only maximum at the bottom. So for that particular section, what you have is the neutral axis is kind of skewed to one side. The stress distribution looks like that. This distance is 4.62, which is almost 3 times, or more than 3 times what the distance at the top is. This stress turned out to be 128 KSI, and the other one will be, what, 1.38 divided by 4.62 times 128. That's proportionate, and that'll be 38 KSI. This was the bending stress. And then the normal stress would be, you'd just add on a tensile stress of 2.12. This would be the N over A. Or rather, not normal, you would call this the axial stress because this is produced by the axial internal force. But both of them are normal, so they would combine straightforward, just add and subtract and so on. Okay, so I chose an unreasonably small size of the cross section, which is why the stress turned out to be so high, but the method remains the same. Now, obviously, some of you are thinking that, will we have to do all this for a 6-minute question? Doesn't seem reasonable. But if you're aware of all the different steps, I believe that the PE exam, most people report that on the PE exam, they have found that, especially for the AM, that if you are looking at 3 steps of calculation, you're pushing it. That's rare. And most of the time, you're getting away with 1 step or 2 steps of calculation. So they'll have to shortcut this a lot, or ask you about a certain subset of this problem. Sometimes they hide this centroid type of thing in a question such as, let's say you have a like a precast beam like this, which serves as the support for a bearing for a girder or something, right? So there's a girder coming in, sitting on a bearing, transferring its load, and we are told that the reaction is whatever, 40 kips, and it transfers it 4 inches off the edge, and they give you the dimensions of all of this, right? They give you the dimensions of this beam, weird looking beam, and they say that this is like 6 inches here and 6 inches here and 8 inches here, and that would be 12 obviously, and this whole thing is, let's say, 18 inches. And they ask you something like, what is the torsion produced in the support in the L beam due to the reaction R? Okay, there's a question from Corey. How did you get the 38 KSI at the top? Oh, I just proportioned it because it's linear, right? So these distances are in the formula my over I. If I'm at a particular location where the m is what it is and the moment of inertia is what it is because it's the overall property of the cross section, my stresses will be in proportion, linear proportion to the distances. So if this distance 4.62 gave me 128, this distance of 1.38 must give me 128 times 1.38 divided by 4.62. So instead of, I mean, I didn't save myself a whole lot of work, but I was just doing it by proportions, and that gave me the 38. Okay. So here they're asking what is a torsion produced in the L beam. Now, why is there going to be torsion? Because this load that is applied to this beam is not at its center. Technically, there is a little bit more to it, but not for the AM. I mean, technically, the shear center is what should be calculated, not the geometric center. But in this case, they are, to keep it simple, they're asking if the centroid of this section is here and the load is here, how off are they? Because if they're off, then not only would it transfer a shear force at the centroid, it would also produce a torsion. Not a bending moment, mind you, it's a torsional moment because it's about the polar axis coming out from here. It's that kind of a load will produce a moment about that axis. So indirectly, it's a question about finding the centroid. So again, you would take that cross section and you would divide it up into one rectangle, which is what, 6 by 8, another rectangle, which is, if this is 6, that is 6, and the height is 18. So because we are interested in the horizontal offset, because that's what's going to cause that moment, right? We are interested in this offset. How much is it? Not the vertical. So we can only confine ourselves to finding x bar. So we can take that to be our datum, and we can say x bar from there is going to be x1a1. Same formula that we had for y bar, but for x's. x1a1 plus x2a2 divided by a1 plus a2. So the first area, if I say that's the first, and that's the second, is area or the centroid is here. X is 3 inches multiplied by the area is 48 square inches plus x2 is here, right? And that will be measured from the same datum, will be not 3 but 6 plus 3. The full 6 going through the first shape and then halfway into the second shape. So 6 plus 3, that would be 9 inches multiplied by the area of that one. 18 times 6 is 108 square inches, right? Divided by the total area of 156 square inches. So that would give you 3 times 48 plus 9 times 108 divided by 156, 7.154. And now we can see that the reaction was transferred at a distance of, I lost my pen. Reaction was transferred at a distance of 4 inches, but the centroid is at a distance of 7.15 inches. So that means that that eccentricity would be 7.15 minus 4, or 3.15 inches. That would be this eccentricity right here. That would be this. And therefore, the torque that we have to design for will be my reaction of 40 kips multiplied by 3.15 inches. 126.2 kip inch, or 10.5 kip foot. Pay attention to units always, because sometimes, I mean, if I were you, I would do this. I would, right from the beginning, I would pay attention to what units are they're asking for the answer, right? And I would try to work with consistent units right from the very beginning. So if the answer involved inches, anything that I have in my problem, I would, in feet, I would convert to inches, and I would just work with those numbers. Sometimes it's a personal choice. Sometimes that's not so great, because especially if you're converting all your feet to inches, imagine taking moments, right? You're going to take moments of a force multiplied by 5 feet. Now, instead of multiplying the force by 5, all of a sudden you're multiplying by 60, and you're not dealing with much bigger numbers. So sometimes people find it convenient to just stick with feet, get the moment in kip feet at the end, and then convert the final answer to kip inch. But don't forget that last step, is what I'm saying. Because if you get caught up in the numbers and the calculation and this and that, and by the time you get there, you forget to get it back into kips and inches, that'll get you off by a factor of 12. A very common predictable mistake is being off by a factor of 2 when there is a situation like, well, let's say you're just supposed to calculate. The best example that comes to my mind right now is one of these wastewater treatment things, where you have these rotating discs where the wastewater comes in contact with the microorganisms on the surface of those discs. But on that case, both surfaces are in contact with the wastewater. So the area that's in that formula is actually the total area on both faces of that disk. So if you calculate pi r squared for the disk, if the full disk is submerged, that is. Usually it's not fully submerged. But if you're calculating using the circle formula, you're only capturing one side, but you have to then double it in that particular situation, right? So what I suggest, and I don't want you to overanalyze this, because sometimes we get hung up on certain things and we waste a lot of time, is when you're scanning the answer choices, the best way to go about the reading and the attacking the problem the right way is, if I have a problem that is very verbose, that has a lot of language, then I will, before I get hung up in all the details, I will first look at the bottom line. What is it that they're asking me? Because if I am aware of what they're asking me for, and then I read the question, especially if it's a very long-winded question, kind of like I'm being right now. But if there are tables and charts and figures and stuff like that, 2 pages describing the question, you want to know in which direction to go to make sense, to pick and choose what's useful out of all that data. Do you know what I mean? I mean, sometimes the environmental questions used to be like that. There is a curve, and maybe you need 1 point from the curve, and there is a table, and maybe you need a single value from a single row of that table. You just have to know which row to pick out the value from. Now, if you know where the solution is going because of how they phrase the question or what they're asking, then it doesn't seem as overwhelming, because you know that you've got to pick out one thing from the table and one thing from the figure, and that's all. They're done. You don't need them anymore. And now you can focus on what to do with those 2 numbers you pulled out from those 2 design aids, right? So get a sense of the question, but before getting into reading word by word, get a sense of the last line of the question. What is it that they're asking you exactly, and how is all this stuff on these pages relevant? And then secondly, make sure that you're aware of the units that are embedded in the answer choices, so that maybe if appropriate, you can adjust your units right from the very beginning. And then while you're looking at the answer choices, this is what I was going to talk about in the first place. If you notice something quirky about the answer choices, for example, let's say there is a 0 amongst the answer choices, right? That 0 force members thing asks you for a member force and a trust member. Let's say one of the options is 0. That at least opens up the possibility that that member could be a 0 force member, and maybe there is a quick way to identify it as such. It doesn't guarantee that it's a 0 force member just because there is a choice of 0 in one of the ABCDs, but at least it opens up the possibility. Somebody has a question? Oh, Rajesh, somebody's mic is open. Hang on. If you can figure out, I can't see anybody. I can't tell whose mic. If you can mute yourself. All right. I lost my train of thought. Hang on. Oh, if there is something weird about the answer choices, like you see that 2 of the answer choices seem to be off by a factor of 12. So there is a possibility that there is a inches and feet predictable mistake there, right? Or they're off by a factor of 2. In other words, there are 2 choices. One is 40, one is 80. That should at least get some kind of a flag up saying that I need to watch out. Maybe there is a lurking mistake, possible predictable mistake there. All right. So it's almost like watching over your own shoulder. But if you get too much into it, then you can waste time. So it's a matter of developing a sort of a habit over practicing over the next couple of months, developing this habit of scanning for these things, but not being over analytical for it, in that you're spending, out of your 6 minutes allotted for that question, you're spending 3 minutes just looking for all these patterns. Maybe there is no pattern in that particular one. But if something jumps out, that should tell you, let's be careful about this particular thing. All right. All right. So as far as axial stress, we don't have a lot of time. Let's talk about one little thing here. We'll start with on Thursday, we'll start with some material properties, especially steel, concrete, the whole thing about, but Hooke's law, another type of question based on Hooke's law for axial stress, is basically says that if you have a prismatic element, in other words, one with a constant cross section, prismatic is constant cross section, subjected to an axial load, let's just say tensile, because when you have a tensile load, you don't have to worry about buckling. The same theory could actually even cover compression, as long as you have precluded buckling, as long as you know that we have prevented this from buckling in all kinds of ways, we have put it in a sleeve or whatever, so it's not allowed to buckle, all it'll do is shorten. Then whether it is shortening or lengthening, the same formula can cover both of those, as long as it's axial stress, axial load. The length is obviously the initial length of the element, and E is the modulus of elasticity. The modulus of elasticity of structural steel, most common grades of steel, is pretty constant. Steel, the default value is 29 million PSI or 29,000 KSI. And so they may, if they are talking about steel, they may just leave this out and say that, well, that's a well-known common value, not too much variation about that, so people will know that to choose it. For concrete, however, modulus of elasticity changes with the grade of concrete, right? The higher the compressive strength, the higher the modulus of elasticity. So they'll have to tell you what grade of concrete you're dealing with for that one. But for steel, they could leave it out. So this is, as you build up your materials, you will find that a lot of things in the notes I sent you, for example, that covers depth for all the 5 areas. Not all of it is relevant for you. You may strip out a whole bunch of pages and saying, I don't need these pages, ever. At the same time, you may, in the process of your practice and reading and so on, you may discover things that are coming up again and again, and that are probably more likely than other things to show up on the test. This kind of thing, you want to make a sort of a crib sheet, for the lack of a better term, of your own where those things are going on. So that's your first reference. If you're trying to look up what's the modulus of elasticity of steel and you just don't remember, but you remember putting it on there, you don't have to go hunting around in your notes or in the book or something, you have it there. The FE handbook summary that I talked about is also a good, even though it's not just a couple of pages, but it's a good summary of a lot of things. But you need to look at it before you actually print it out and take it with you to the test, because if you're not familiar with how things are laid out and how they are written, for example, the fluid mechanics portion of the FE handbook I don't like at all, unlike most of the other areas are written pretty well. So if you're aware of that, for example, let's say you agree with me and you look at the fluid mechanics section and say, why is this written like this? Then you don't want to use that portion of the FE handbook for fluid mechanics, but maybe the hydraulics portion is written really well. So you don't want to be surprised at the time of the test is what I'm saying. You should go through it before, but I find it very useful, the FE handbook. The portions from the general section, for example, what we're talking about now, mechanics of materials, there might be a couple of pages from mechanics of materials that you print out to support the structural portion, and the environmental section may be relevant to, not maybe, is relevant to those who are doing the water and environmental depth, right? So there, it's good stuff. So a typical application of Hooke's law will come into something like, they give you a beam, let's say, and they say that here's a beam, it's supported by a cable, it's a steel cable, diameter 1/2 inch, length 36 inches, and this end is restrained by a pinned support, and you have a load here of 20 kips, and this is a rigid bar. Calling this bar rigid implies that nothing is rigid, infinitely rigid. In other words, everything will bend or break or deform. But calling it a rigid bar basically implies that compared to the other things in the structure, it is rigid. Meaning that when you apply this load, this bar will not really bend, it will deflect while remaining straight. That's the implication of the word rigid, right? But of course, if you applied a larger and larger and larger load, at some point you'll start bending this bar. You'll start bending it because it's got support on one end, support on the other, and load in the middle. But what we are saying is the cable will stretch, but the bar will not really bend that much. So if you look at that free body diagram, and if you call these points A, B, and C, and if I take summation of moments about A clockwise positive, then we'll say something like, well, I'll need dimensions again. Let's say this is 8 feet and this is 6 feet. So I'll get something like 20 kips times 8 feet, that's clockwise, minus the cable tension T times 14 feet is equal to 0, right? My free body diagram looks just like there's reactions here, which won't matter if I take moments about here. There's a 20 kip load here and a tension force here. Cable can't develop compression, so it'll always be tension, so it'll always be pulling away from that connection point. And so this will give us T is equal to what? 160 divided by 14. So that'll be 11.43 kips. And then if I want to figure out the extension of the cable, the delta L for the cable, the formula is PL over AE or whatever. This is the force that causes that extension. So it's going to be 11.43 kips multiplied by the length of 36 inches divided by the cross-sectional area pi over 4 times 0.5 squared. By the way, pi r squared pi d squared over 4, same thing, but pi d squared wrong, pi r squared over 4 wrong. So don't get them mixed up is what I'm saying. Very often for circular elements like rods and ties and cables and so on, the diameter is specified. But if you're used to always doing circular cross-section as pi r squared, make sure that's reduced to a 1/4 inch and then plugged into the formula. Or you can use pi d squared over 4, right? Predictable mistake, a factor of 4 mistake there. Multiplied by 29, I'm going to use 29,000 because this is kips, so I want to use KSI, not PSI. So that'll be that times 36 times 4 divided by pi divided by 0.5 squared divided by 29,000, 0.07 inch. Now in this case, the nearest number is what you're looking for. There is no reason to go up or down. But if the question was phrased like, if the maximum allowable deflection on the cable is 0.1 inch, what is the maximum force you can put on here? You can just put a different spin on it, just turn the question around. Alternatively, if the maximum allowable deflection at C is 0.1 inch, what is the max load P? Then you can go backwards, but you have to make sure that if you have to say something like this, delta, which is TL over AE, must be less than or equal to 0.1 inch, which will lead to a condition like T must be less than or equal to something, which will lead to a condition which is P must be less than or equal to something. When I say P, I mean the applied load. So here is applied load P, and here is the tension T. These two are related to each other, right? P times 8 feet is equal to T times 14 feet. That's what we saw from our equilibrium equation. P times 8 feet is this moment, T times 14 feet is that moment. They must be equal. So P and T are equal. So once you have a condition T must be less than or equal to some value, that automatically translates into P must be less than or equal to some value. So once you calculate this, remember that the answer you choose must be below this value. You can't go higher than this value. You go higher than this value, your deflection will be more than 0.1 inch, which you are not allowed. Okay, should we stop there? I ran over a little bit. And then we'll try to finish out structural. From everybody I've heard back from, structures is one of those things that people consider. They look at the side of Lindbergh's book, for example, and they look at that black shading and they see that the structures portion is 3 times as thick as anything else because it's just got so many elements to it, structural steel design and concrete design and so on. So people who don't do structures as a regular thing that's the one that they're most afraid of in the sense that they don't like it or they're not familiar with it and they think that's going to take a disproportionate amount of work. But those very same people come back and tell me that they were very pleasantly surprised by the structures questions that show up on the AM. So they stay pretty tight. NCS stays pretty tight with the AM portion and keeps the structures questions pretty simple. Basic statics, basic strength of materials, very basic structural analysis. That's all you need. You don't need anything beyond that. So for us to cover that ground, 2 lectures is more than enough. So we'll try to do a lot more problems on the next class, but we need to talk about some of the materials, properties, and so on before we do that. Good enough? Okay to stop there.